Hi, everyone. Just a quick note about today's show. It is a live show, and the meeting for the American Association for the Advancement of Science is loud and proud, so please don't mind the crowd noise. We promise our guests this week are worth it. We've snagged 3 amazing experts to talk about microplastics, rafting barnacles, and bird poop, because at Science for the People, there's always room for bird poop.
Thank you. Okay. So, we're about to get started, and the way this works, for all of you people who are enjoying Science for the People the first time, Science for the People is an interview-only podcast, and so I'm going to give an introduction, and then I'm going to start asking these fabulous scientists questions about plastics, and it's going to be depressing and amazing, and I brought this plastic coffee, and I feel bad already. I'm just going to, don't look. Okay, so... welcome to our Science for the People live show. Thank you. I'm Bethany Brookshire, a science writer at Science News and Society for Science and the Public, and today I am delighted to be here on the podcasting stage at the American Association for the Advancement of Science. And when we got the invitation to record a live show here, I just started digging through the program, and it's so wonderful to be here. It's like an embarrassment of riches. In terms of content, but a couple of the sessions really stood out to me, and all of those were on plastics. We are surrounded by plastics. Right now, there are plastics in my coffee. There are plastics in our smartphones. There are plastics in the chairs you are sitting on, the clothes we are wearing. Plastic wrapped the food you probably ate for lunch. If you ate lunch, please eat lunch. And that plastic eventually ends up in the environment. And as scientists have found, a truly shocking amount of it ends up in the ocean. When a lot of us think of ocean plastics, we might think of like whole plastic bottles and tennis rackets and, I don't know, boats, big chunks. But a lot of the plastic in the ocean is actually way smaller than that. These plastics are microplastics, which are smaller than 5 millimeters in size. That's about half the size of a Lego, give or take. I should have brought Legos. But small plastics can have big effects. So today, we're going to talk about plastics in the water, where they're going, how much there is, how we track it, what on earth we need to do about it, and I'll just go ahead and tell you guys right now that they found plastic in the beer, so we'll start there. So, to cover this incredibly depressing topic, I'm here with Jennifer Provencher, Chelsea Rochman, and Christina Simkanin. Jennifer Provencher is unit head of the Wildlife Health Group at the Canadian Wildlife Service. Chelsea Rochman is an aquatic ecologist at the University of Toronto, and Christina Simkanin is a marine ecologist at the Smithsonian Environmental Research Center. Thank you all so much for being here, even though I know that there's another session on plastics right now, and I'm sorry.
Okay, no problem. Yeah, thank you for having us.
So I wanted to start a little bit with the scale of the problem. Chelsea, do we know how much plastic is in the ocean by weight or volume or tanker trucks, blue whales?
So we don't know how much plastic is in the ocean in terms of in general. We have some estimates of how much is floating on the surface of the ocean, and we have estimates of how much enters the ocean every year. So the number that we're often given is that we estimate, and this comes from Jenna Jambeck's work, that 8 million metric tons of plastic enters the ocean each year. And so the elephants or the blue whales is that if we lined people up along all the coastlines around the world, shoulder to shoulder, and they all had 5 plastic bags and they threw them all in at the same time, that's how much enters every year.
Oh.
And so you can imagine that accumulates to a much larger amount.
So that's a terrible picture to think about, but obviously we do not go around deliberately tossing plastic into the ocean. Of course, people do that because people are terrible, but for people who are not terrible, when we talk about how the plastic gets there, how is it getting there? I think a lot of people think that plastic gets there through rivers or whatever. How is this plastic getting into the ocean?
So many ways. So plastic gets into the ocean, and this is something we try to understand a lot in our lab, is there's many different transport pathways for it to get into the ocean. One is if we don't have waste management systems where somebody collects the waste at your house and takes it to an engineered landfill or takes it to a recycling center or to a compost facility, it can end up in the environment. That litter, when it rains, can go into, everyone's on a watershed, it can go into a river and enter the river that way. It comes through wastewater treatment plants, so the microbeads that we wash our face with, they go down the drain, they can end up in the water that way, or the fibers from our clothing. Fishing gear, sometimes scientists accidentally lose a zip tie off of a research cruise. We hope that never happens, but it does.
Or an entire research buoy. Some of those.
Or an entire research buoy. Sometimes we do that on purpose. So, I mean, but the point is there's a lot of different sources, and so when we think about how do we prevent it, we have to think about all of the different, I guess, pipes that we can shut off.
And I have to ask, because it was a big deal last year. There was a sea turtle with a drinking straw up its nose, and all of a sudden there were many articles about drinking straws and how evil they were, and then there were articles about how people who wanted to ban evil drinking straws were evil, and so forth. How much do drinking straws contribute? Do we have a percentage?
So we don't have a percentage, nor do we have a number, but I think that they've been a great gateway to talking about the use of single-use products. And so around the 1950s, when we started making this material, we were producing about 500,000 tons per year. Today we produce more than 380 million tons per year, about half of which are for these single-use items, unfortunately, like your coffee cup. But it's okay, it's got a sippy cup instead of a straw. But these single-use items are not always recycled, and sometimes they don't always make it into the bin. And so I think straws are a great gateway for talking about how we can reduce the use of single-use when it's not necessary and think about more sustainable. So I think it's not just about the straw, but the straw has been a good way to have a conversation about it.
And we were talking about, whole drinking straws. This original photo of the sea turtle, it was a whole drinking straw. It was really awful. Actually, don't Google that. But most of the plastic that we end up actually talking about, these plastic fragments do get smaller. The ocean, in the words of one of my favorite people, Miriam Goldstein, the ocean will wreck your things.
We were just talking about her.
Yeah,
She's
the
wonderful.
ocean will wreck your things.
Yeah.
And so how much does it wreck your things? Will these plastics eventually entirely degrade? Will they ever go away?
Yeah, so good question, and segue back into Miriam Goldstein. So when I got interested in this issue, I'd heard about the garbage patch, which was described as this patch of big things, the whole straws and the bottles floating around in the middle of the ocean. And the first time I went and visited the garbage patch was with Miriam Goldstein. We were bunk mates. And when we got there, we realized that it's not an island of big straws and bottles and things like this. It is a soup of tiny little bits of microplastic debris. And so by nature of that, the fact that the majority of what's out there is actually small because it has been broken down over time, I have accidentally spent my entire career, which hasn't been that long, but studying microplastics. So yes, the ocean will wreck your things, and it makes, I think, by count, the majority of what's in the ocean are these smaller bits.
Do they ever completely go away? Is that
So eventually they will completely go away, but we do not know how long that is. For plastics, a big polymer of carbon and hydrogen and all of the building blocks that go into it to come back down to those individual units takes maybe decades to hundreds of years. And so this is one of the reasons why we think that even plastic that entered in the 50s is still around, and these numbers are just accumulating or growing over time.
And as you mentioned, they get smaller, they become these little microplastics. And they end up, because they are micro, they end up in living things. What kind of organisms tend to end up with microplastics inside them?
So I would flip that question on its head. What type of organisms don't tend to end up with microplastics inside of them? I'm sorry to say, but it tends to be that as we look in fish and zooplankton and whales and I don't know, name your turtles, name your taxa in the ocean. We tend to find them. Obviously, they're not in every animal. They're not in every species. Depending on where they live, they might be exposed to more. But the prevalence of microplastic is such that we find them at every level of the food chain. And so, again, it usually comes down to where don't we find them versus where do we find them.
And that includes, of course, the organisms that we eat. And you have a 2018 review on microplastics in your seafood. So are we taking in these microplastics, and in what amounts should we be looking for small plastic bits in our poo?
Well, I don't know what you want to look in your own poo. That's entirely up to you. But I didn't mean to rhyme. But yes, so it is.
Don't diss my hobbies.
It is in the seafood that we eat. But I think more importantly, one thing to think about is that if it's going to get in shellfish, it's going to be in the food that we eat. If it's in fish, we don't tend to eat the guts, so that may not be a big source. But as I've learned more and more about this, I don't think seafood is the main route by which microplastic gets into our diet. So we know that it's in drinking water, and it's in the dust around us. We're sitting in a room with a plastic tablecloth and plastic carpet, and if you look at the sun shining through a window and you see all the dust particles, you have to wonder how much of that are microplastics. And as I sit there eating my fish, they're falling on my plate. So when it comes to human exposure, yes, we're exposed. How much, we're trying to understand. Seafood's probably not the greatest route, and whether or not it affects us, we have no idea. So we still have so much to learn about how the use of this material may impact us when it does come back to us in a meal.
So we've been talking a lot about microplastics in the ocean. But some of the first findings about microbeads in aquatic environments, which, by the way, actually made me completely change my face wash to face wash that didn't have microbeads, was because I found out that microbeads from things like face wash were ending up in the Great Lakes. Mm-hmm. So fresh water is also an issue. And, of course, plastic often goes through fresh water on its way to salty water.
Yeah.
How much of plastic debris ends up in fresh water?
So I can speak to the Great Lakes. So Matthew Hoffman, who's a researcher at the Rochester Institute of Technology, thinks that about 10,000 metric tons of plastic enters the Great Lakes every year. And so going back to how much we see in fish, in the ocean we find plastic in about 1 in 4 fish when I've looked. In the Great Lakes we find plastic in every single fish that we open. And so the amount of plastic in the Great Lakes, by nature of being a freshwater body of water, less dilute than the ocean, surrounded by big urban centers, have really made me think differently about this issue, in fact, and I spend 90% of my time now in freshwater thinking about this issue.
And one of the things that particularly struck me reading your work was how much plastic ends up in specific organisms like bivalves. Why are those particularly bad?
Why would it end up in a bivalve
Yes.
more than? Well, I think it has to do with the way that they feed. So some of us are choosy about what we eat and picky, and some of us are more generalists or don't even choose and just imagine just opening your mouth and taking what lands in it. And bivalves are filter feeders, and so they're just sieving through the water, and by nature of it being there, they're going to be exposed. Whereas if I'm an orca whale and I'm choosing the food that I eat, they may be less exposed directly to eating a piece of plastic.
And we now know that plastic is ending up, for example, in our oysters.
Which please keep eating oysters.
And our beer and our honey. And it's too late. I'm never eating an oyster again. And I'm switching entirely to liquor for my nutritional needs because I figure that's at least distilled. But we aren't the only things that eat seafood. Seabirds eat seafood. Heck, it's not like they eat much else than seafood. And that means they are eating the plastic too. So, Jennifer, what do we know about how many species of seabirds have been caught eating actual, literal junk food?
Yeah, it's a good question. So you can imagine that seabirds are the true oceanic feeders, and many species of seabirds feed right at that surface water-air interface. And so there are some seabirds that are specialists. You can imagine like albatross or the bird I work on, northern fulmars. They have those beautiful long wings, and they are just cruising over the surface looking for fish and plankton. And they don't dive very deep. They are dependent on that surface interface, which is exactly where a lot of the plastics actually sit in the environment. And so there are some species that are highly vulnerable to ingesting lots of plastics because their buffet table, which is the surface of the water, used to have plankton and fish and squid, and through microplastics has now been littered with microplastics. So their buffet is no longer the seafood buffet, but it's plastics and seafood who then also have plastics in them. So they have this mixed buffet table that is up to offer for them. But you can imagine there are other species like penguins and another species I work on, murs or ducks, that are divers. And so they're either eating in the water column somewhere, or they're eating at the bottom of the ocean or in the coastal environments. And their buffet table is more pelagic fish, herring, and then things like mussels and oysters who are actually quite far down. And so they're not, their buffet table is not as littered. Their buffet table is not where the plastic accumulates. And so those species actually have very little plastics in them. So, broad scale, we're talking studying over 200 species of birds that have now been found to have some level of plastic in them. But for a majority of them, the ones that we've looked, so for eider ducks, for example, I've looked in over 300 eider duck stomachs for plastics, and I found one piece in one bird. So not
go ducks.
Yeah, go ducks, exactly.
I'm so proud of them. I don't even know them, and I'm proud.
And so for that, it still gets counted in that 200 species, but at an individual level and a population level, it's not a big deal. Plastics is not the big threat. On the reverse side of that, we have albatross and fulmars and shearwaters who are feeding at that buffet table surface with littered with plastics. And those species also have plastics, but they have high levels of plastics. And some of those species, upwards of 80 and 90% of the individuals we've looked at have some piece of plastic. So you can imagine if all of us in this room were ducks, one person would have plastics. Whereas if we're all albatross...
Did you have to pick her? That was me.
Sorry. But imagine if we're all albatross in this room, including all the people who are at the exhibits, right? Actually, the only people in the room who wouldn't have plastics are the people who are sitting right in front of us. But everyone else in this room does. So it's very different depending on the species and depending really on what they eat, whether they go to that buffet table littered with plastics or whether they go to the buffet table that doesn't really have a lot of plastics in that part of the environment.
Are birds, when you say that they're feeding a lot at this air-water interface, are they picking up this plastic deliberately? I know a lot of birds are sometimes attracted to things that are red, or do they selectively choose this plastic? Do we know how they're taking it in, or is it just kind of passive?
It depends. And I know that that's a hard one, but seabirds are this really diverse group of birds. So you can imagine everything from gulls that you can see in a parking lot at a restaurant to albatross, which never come to land except for every other year where they breed, and there's all these species in between. And so it really depends. So there are some species like phalaropes, which we actually think are opportunistically or more likely to pick up white plastics than anything else because they look like plankton. So we see that they have these really high levels of white or light plastics. There are some people, and there is some work looking at some of the chemicals that they think they're being attracted. So you can imagine there's biofilms and other things growing on the plastics. And if there's a bird group like albatross and Procellariforms, these tube noses, they literally smell their food. And you can see this in real life. If you've ever gone on a seabird watching cruise, what you do, especially when you have students on board and you really want them to see a seabird, is you just drop a few drops of cod liver oil off the back of the boat, and you just keep going. And you can actually look out on the horizon. You can imagine, so the boat's going one direction, you're looking off the stern, you drop the cod liver oil in, and you can watch. And within minutes, you see these birds come in, they fly over your route, and then they fly up the trail right to your boat. They smell it. And 5 minutes ago, there's no birds. You just I swear there's birds out here. Just wait, give it 5 minutes. And so you can imagine that if there are plastics that have organisms growing on them and biofilms, that the birds could be attracted to them. Whether they eat them directly or indirectly, it's difficult to say. There is some evidence where they've looked at the peck marks on cuttlefish bones, which is a natural food item in the environment, and then the peck marks on styrofoam, and they're identical. And so that does give us some evidence that the birds are not only targeting the prey, but also the plastics in the environment. But then there's also lots of questions of, are the birds eating the plastic, or are they actually eating the fish that have eaten the plastics, and what does that look like? And those are really hard questions that we're still trying to tease apart. But there are observations, again, from cruises of birds actively feeding in kind of little whirly pools of plastics. So I would say that both is happening. From a toxicological perspective or an effect perspective, it doesn't really matter. Because what we know is that the plastic is going in and then staying in their stomach. And what we're interested in from a health perspective is whether or not it matters. Not necessarily whether they got it because they ate it or because they ate a fish that ate it.
So you're talking about plastic in bird stomachs. And actually for your research, you looked at bird digestive tracts because your job is fun. Where did you get these birds?
Yeah, Yeah, and that's a really important question. So we, in my kind of research world and group, we get birds in two different ways. Sometimes we get birds who what we call a wreck. They wash up. They're beach birds, and so you can imagine just through life, birds die at sea for multiple reasons, and they sink in the ocean and get scavenged, but they often then wash up onto the shore. And so we work with volunteer groups, Bird Studies Canada, volunteers that find those birds, collect those birds, and then we can look in those birds. And that's how a lot of the work is done in around the world, looking at beach plastics. The other way that we do it, particularly in my group for a lot of the species we look at in northern Canada, is we work with Indigenous partners. So we actively work with Inuit hunters who go out and collect those birds for various reasons. And then, similarly, they may eat or take tissues, but they're not taking the gastrointestinal tract. Typically, we don't eat the gastrointestinal tract. And so I work collaboratively with hunters who do sampling, and then I take those gastrointestinal tracts and then can look at them for ingested plastics.
And so you work with the Inuits and other native groups who actually are able to hunt these and eat them. Have you eaten one?
I have eaten seabird.
And?
It's very good.
Is it? Is it like chicken?
It depends. It depends. It depends on the species. It depends on a few different things. It depends on what time of year you get them in. But broadly, we think about it as a bird. So we think about it as this white meat. And if you actually, the screen was a little small this morning, but in one of the slides I showed we were dissecting a bird, and there was a teacher who was actually cutting up an eider duck breast meat as we were kind of putting all the other samples into the jar, and it actually was red. It's very red. It's a very dark meat, and ducks are typically very oily, and so the ducks for sure taste like the duck that we're used to. It's a very dark meat. Some of the other seabirds that are more, I would say, oily, they definitely have a different texture to them, but they're very good. I would say that depending again on what their diet is, right? We are what we eat, and so depending on what their diet is at the time, they can have strong taste and they can have not so strong taste. And to kind of also put a spin on it is we know that some of these birds, even within species, some can be specialists on zooplankton and other individuals can be specialists on a type of fish species, and then there are generalists who just eat whatever they want. We know that from our diet studies, and so it really depends.
I have to say, if you are what you eat, then I'm about half coffee and half Pop-Tarts by mass. But, it probably varies. So you did work with native groups. Do you build, relationships? Is it a very equal, what kind of stake do they have in your research?
Yeah, it's a good question. So I work a lot with our Indigenous communities in Canada and the Inuit in particular on plastics. And we come at it from very different questions. And so there's this question evolving, I think, where how do we include Indigenous knowledge and how do we include science to answer these emerging questions? And the way I try to phrase it and talk about it is specifically for plastics, our relationship between Indigenous knowledge and science is what I call the give and go model. So just like in soccer or hockey, right, you pass the ball or the puck and you go a little forward, and then you might see a defender and you pass it back to your partner and they take it a little bit farther, and then it's give and go, right? It's give and go, but you're collectively moving these questions forward. So in the case of plastics, we very much have this give and go collective relationship. And so through hunter-collected samples, we were able to access some of the first stomachs that we were able to look for in plastics. The community members that we worked with were not particularly concerned. That wasn't the purpose of the collections. It was actually other contaminants that we were interested in. But we were able to then take a look at plastics. We report back on an annual basis. We actually have a trip to go back in a few months where we report on our findings. We reported back on plastics, and the communication, the dialogue was, we're really interested in that. We want to know more. What about these other species? And so then we started testing the other species and using traditional knowledge and indigenous knowledge to figure out, well, what are the species that are going to be the most vulnerable to ingesting plastics? And so, we worked with them a little bit in terms of figuring out what species, and then, we then, in the same room or the same space, we moved along with standardized methods at the international level. We worked towards looking at which plastics and polymers were there with partners and chemists, what are the contaminants associated with these plastics, moving this along. At the same time, our Inuit partners were integral on getting plastics on the research priorities list within both the federal level and the territorial level, which allowed us to then apply together and do more work on it. And so there's this really give and go relationship where there's lots of questions that they're interested in from a food security perspective and a contaminant perspective, but then we're also able to move a bunch of other kind of balls forward that more the international community is interested in, like standard methodology to compare across space and time.
And this is the point where we are going to go on break. And when we get back, we're going to talk about not poop, but pre-poop. There's a difference. We'll be right back.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skeptic Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
Okay, welcome back. I'm Bethany Brookshire, and I'm coming to you live from the American Association for the Advancement of Science meeting in Washington, D.C. I'm here with Jennifer Provencher, Chelsea Rochman, and Christina Simkanin, and we are talking about microplastics in our water, in our food, in our seabirds. And Jennifer, we were talking about bird digestive tracts because you have obtained birds and you look in their stomachs, and I wanted to ask how many times you have now been pooped on for the sake of science.
Wow, I don't know if I can count that high. So you have to imagine that birds in the Arctic don't nest horizontally, they nest vertically. And so what I often talk about is below the polar bear line, birds nest like this, right? They can kind of spread out. So if you go to colonies in Newfoundland or in BC, they kind of nest out in the horizontal landscape. But what I affectionately refer to as the polar bear line, birds cannot be that vulnerable because the bears just walk by and eat them. And so they nest vertically. And so you can imagine so when we're studying birds, you can imagine that to access a vertical face, you have to be a climber. And so I've spent a lot of hours dangling on a rope in the middle of a bird colony, and you literally look up. There are thousands of bird bums above you. And so one of the first summers I was there, I was in the middle of the colony, and you have to picture me. It's in the Arctic, it's in the summertime. You need to do this on a not a windy day and not a rainy day because you don't want to disturb them or get them wet. But you are in full rain gear because we call it the poop gear because you don't need it for the rain. It's sunny, it's warm, but you are in the poop zone. And so you're, head to toe in rain gear, you've got a helmet on, and you're just kind of hoping that you don't get it in too many places. And the first time...
Please tell me you're wearing goggles.
You can't.
Oh, no.
Because then they get pooped on and you can't see. So you could, but then for the, it's only going to work for like the first 5 minutes, and then you can't go, you have like little wipers. And then you also have to remember that you're basically, like on dry days, and if it's been dry, there's this dust. There's this like poop dust circulating in the air, which is also occurring. But one of the first times I was out on the cliffs, you kind of try not to look up, and you try to just, focus. And you're in there for hours, right? Because it's quite the gear, right, to get into the middle of the colony. But you kind of commit. You're not, you make sure you go to the bathroom, you got some granola bars on you, because you're not just like popping up for, a quick break. And I was working, so you've got your head down, so you can imagine I'm kind of bracing on the cliff, and you've got a rope, And the point of being there is to band the chicks. And so there's all these little baby chicks, and the parents are kind of flying away, and they don't like you. And you're going in, you're picking up these little fluff balls that fit in your hand, and then you've got to take your gear from your belt, and you have a metal band that you're individually putting on these birds, and there's this kind of weird angled twist thing you got to do to cinch it around their little tiny legs. And then you need to put them back on the cliff, which is, the size of an end table, and make sure they don't fall off, because they got to stay there, because Mom and Dad are going to come back. And you're so focused, but one of the things I didn't think about is that the back of my neck was exposed, and about halfway through the day, I just felt this, splat, and then it ran all the way down my back.
I'm sorry, but that's really funny.
And it's just kind of that is what happens, and that's okay, and and so I've been pooped on a lot. Is the moral of that story.
But actually, when you gave your scientific talk about this earlier today, you mentioned that poop was not what you were after. You were after pre-poop.
Yeah,
the platonic ideal.
Yeah. So in a perfect world, so for a lot of our science right now, we do depend on dead birds. And so they either need to be washed up on shore or harvested birds. And in some species, you can actually do something called lavaging or water offloading, where you, again, stick a tube down their throat and kind of pump in a whole bunch of water and make it come back up. But these are not, you need to, you got to catch the bird. You can't necessarily do large samples. If you're interested in endangered species, you can't really do a lot of that. So we're on the hunt. We're actively on the hunt for non-lethal sampling techniques. And so we had this idea, wouldn't it be great if you could just get some poop? If you could hold the bird. A lot of birds, you don't know this, but a lot of birds, when you catch it, it has this fight or flight thing, and they just poop. There, it's easier than it sounds, but you can actually get them to poop in a bag often, which is super useful. And so we thought of this idea of imagine we could just get a poop sample, and then that would be a non-lethal indicator of their plastics, which is in their stomach. And so I thought, okay, well, we can test this out because we've got harvested birds. We have the plastics. My student, Florence Poon, looked at all the plastics in their stomach. We had quantified it. We calculated it. But then we also had their intestine. So we've got the stomach load, kind of the ball where you do a lot of the digestive stuff. But then you pass through the pyloric sphincter and you have this intestine. And so we were like, okay, well, we know it's here, but what's actually coming out the other end? Can we see the plastics in the poop? And so we took the last 10 centimeters of the intestine and actually looked at that for microplastics, and we worked on that. And, I was calling it poop for a long time, or the feces, and we went for a review, and I was very correctly corrected that it was not poop, it was pre-poop. It's the moment before the poop comes out, but technically it's not poop. So in the pre-poop samples, we were finding those microplastics. And again, it's just trying to figure out, what is going in, what is coming out, and then what matters. And again, the findings of that story is that we know that there's microplastics coming out in the pre-poop, but what is most important is that the pre-poop plastics do not correlate with the accumulated plastics. So we cannot use it, as we had hoped, as a non-lethal indicator. And the reason why is that the accumulated plastics represents potentially months of accumulated plastics, and it's 90% fragments. The pre-poop plastics are much more of a snapshot in time, and it's almost all it's almost all fibers. And so the problem is the time scale. So here you're looking at months of accumulation, and here you're just kind of looking at what's happening over a short period of time, because it's just, you can imagine your digestive system it just keeps moving along. And so they don't really match on time scales. And so we can't use the poop or the pre-poop to determine whether the birds have plastic. Some of the birds who had pre-poop plastics had no accumulated plastics, and lots of the birds who had plastics in their stomach had no pre-poop plastics.
Now, one organism's trash, whether it's accidentally ingested or not, is another's life raft. Some of the plastic trash floating in the ocean can serve as boats if you are small enough. In fact, after the 2011 Japanese earthquake and tsunami, some organisms used plastic trash to travel more than 7,000 kilometers across the Pacific to the United States and Canada. And Christina, you studied these inadvertent tsunami refugees. Why were you looking at whether organisms could make this trip?
Firstly, because it was just so fascinating and interesting that species could travel for that long of a distance and for that length of time. So previously, scientists thought that coastal organisms couldn't survive for long periods of time in the ocean. So it was thought that they could maybe survive for about 2 years based on the amount of food that was out there and sort of high UV radiation levels that might kill them while they're floating. But data from the tsunami debris that landed on the Pacific coast of North America basically showed that these coastal organisms could make it across the ocean for 5, 6, 7, we're going on 8 years now, and some Japanese species are still arriving on debris that can be traced back to the tsunami.
Which is, like, what do they eat while they're floating out to sea in some place that's not their habitat? It's got to be like going to space. What are they eating out there?
A lot of them are filter feeders, and so it's a good question. They're filtering the water, so they're eating zooplankton and phytoplankton that are in the water column. But how they're able to survive for that long of a distance in coastal or oceanic waters that are thought to be less populated by zooplankton and phytoplankton species is a good question. We're trying to figure that out, actually, how they survive for such a long period of time in the ocean.
And so you actually looked at debris from the 2011 tsunami and looked at what was kind of transferred over. How did you collect the debris, and how did you determine it was from that time period? Like, how do you tell? Are you looking for like things written in Japanese on the trash, or are there other ways?
Yeah, so I should clarify, this isn't my work. This is work that was led by Jim Carlton and some of my collaborators. But yes, so basically tracking the origin of debris is really difficult, which is partly why the debris from the tsunami was so fascinating, because they were able to track the origin. But they used identifying characteristics, so Japanese writing, some of the boats and beamwood and different things that arrived had sort of location markers, or some of the large docks that arrived had literally names on them.
So whole docks arrived?
Yeah. So
intact?
Whole docks, yeah. One whole dock arrived off the coast of
Washing up?
Oregon, yeah.
Wow.
3 were dislodged from Japan, and they knew they went missing. So massive docks, essentially, that had over 100 live organisms on them once they arrived all the way across the Pacific. There was a second dock that washed up off the coast of British Columbia or Alaska, but it was kind of in an area that was really low population, so it was much more challenging to sample. And then the third dock was seen off of the coast of Hawaii, and then they lost track of it, and it's never been found again. So it's still either missing or washed up on a beach where very few people ever go. So it's out there somewhere.
And you're talking about whole docks. I mean, I kind of assumed that most of the stuff washing up would be microplastics. Is it all sizes?
Yeah, it's all sizes, and actually most of it is not microplastic. So it's above 5 millimeters. Is that the size for microplastic?
Yes.
Yeah. So most of it is larger pieces of plastic, because in order for an organism to survive such a long distance, it needs to have sort of areas to reproduce, and some of the debris that washed up was actually whole boats, and boats that had water in the hulls, so they essentially brought aquariums of species across from Japan. So they would
with whole fish.
With whole fish. So literally an aquarium where, like, essentially a tiny ecosystem that survived for 7,000 kilometers and years of just like trophic interaction. So the algae and the fish were just living in harmony in this small space while afloat across the ocean. It's amazing. Yeah.
Yeah, I keep thinking, this is a 7,000 kilometer journey, and I keep thinking, what's a comparison of something that's 7,000 kilometers? And then I'm like, that's the width of the Pacific Ocean.
Yeah,
There's
huge.
no other comparison. That is the Pacific Ocean. And so you mentioned years. How long did it take before the first pieces started arriving? Are things still arriving?
It only took a year. And things are still arriving, yeah. So there's these pulses at the end of winter and the beginning of spring, when debris starts to wash up along the shoreline. And that started within a year after the tsunami. The first pieces of debris arrived, and that's kind of when scientist Jim Carlton specifically was like, this is really fascinating, interesting. We need to start coordinating and get people who are walking on beaches and different, state and provincial managers to be out looking for these debris items. And they basically brought in anything they could, tried to determine whether it was from Japan or not. And then if they could determine that it was most certainly from Japan, then they would ID, take all the species off and ID whatever they could, using a whole team of taxonomists around the globe.
And you mentioned more than 100 species. How many species have been found so far?
So Jim Carlton spoke this morning and he gave a new number because more debris has been washing up. So new species have been identified. I think the new number this morning was 379, so 379 species
That's a good
so
number.
far have been reported. And that's from about maybe 700 pieces of debris only. So it's likely that a vast number greater than that of debris actually arrived, but couldn't be traced back to the tsunami or was never found. And so the estimate of the actual number of species that arrived on debris is actually much higher.
And what kind of organisms? When people think of the ocean, they think of fish, and there were, in fact, fish.
Yeah.
But what kind of organisms mostly ended up attached to this debris?
Yeah, algae and marine invertebrates primarily. So, you have gastropods like mussels and limpets and snails, and then lots of barnacles, some ascidians, which are sea squirts, so marine invertebrates, bryozoans, lots of soft, squishy stuff. A bryozoan, they call it like a moss animal, so it almost looks like green moss. They grow in like a tree-like form, but they're animals. They're amazing. They live in colonies, so there's many of them on one tiny little piece of bryozoan.
And were these all like adults? Were some of them like different life stages of these animals, or?
In some cases, so they tried to age them as much as possible because one possibility is that the debris would get close to shore on the Pacific coast of North America and then pick up species from the Pacific coast rather than Japan. And so to try to differentiate species that kind of accumulated on the debris as it moved close to shore and species that originated from Japan, they looked at like age classes and sizes. And so most of the species that landed and were identified to have been from Japan were older. But some of the...
Well, they've been at sea a while.
They had been at
yeah.
sea for a while. But some of the populations, like Mytilus galloprovincialis, so it's a mussel species that's originally from the Mediterranean, introduced in Japan, also introduced in North America. They were able to see that it had been reproducing, and there were different size classes on the plastic debris. So it had been reproducing the whole time that it was basically crossing the ocean.
I keep thinking of these animals as like kind of being in like a spacecraft, like at sea in this spacecraft, and then so now I'm thinking, oh, these mussels have been reproducing, so it's kind of like they've been having sex in space, except they're having sex in a gross boat in the middle of the Pacific. Anyway,
a love boat.
A love boat. Oh, that's much better. Now, it's one thing to get across an ocean, and it's another thing to kind of actually take up a residence when you get there. Do we know if any of these species have managed to, like, hang out?
So far, no. So Jim this morning talked about the Japanese fish species, that the one that came over on the boat. They've now found a couple of individuals living solo along the coast off of California, and so it's possible that this species is now becoming established, but it's still unknown whether it's been able to reproduce and establish a new population or not. But some of the work that I did in collaboration with Jim this year was looking at a subset of the species that came over on debris and whether the environmental conditions, so the temperature and salinity of the water on the Pacific coast, was suitable for them to establish. And so for species to, land in a new place and actually create a population and be there, the conditions need to be right. So we were looking at what subset of species might potentially establish on the Pacific coast.
And how many of them ended up in places that were okay for them?
Yeah, so we were only able to model 48 species, partly because you need really good global occurrence records, and those data are limited for a number of organisms. But of the 48, 13 landed on debris in locations that are well-suited for them. A further 21 landed in locations in British Columbia and Alaska which are environmentally suitable for them, but they weren't collected on debris there. So a lot of debris wasn't collected from those areas, partly because they're not as populated as Oregon and Washington, which is where most of the debris was collected from. So yeah, a fairly good proportion of the species were suitable.
And this was mostly after, this is all debris from a very large catastrophic event.
Yeah.
The 2011 tsunami was huge. But the ocean is moving all the time, and people are losing things at sea and on the coast all the time. Does this happen all the time? Is this a significant uptick from previous establishment of species from other areas?
Yeah, we think so, actually. I mean, and this kind of helped us enumerate that that's possible. So, yeah, like you said, we know plastic is in the ocean. We know species can travel on it now. Plastic lives for a long period of time before it starts to biodegrade. And this vector likely could be spreading species much more often than we think. It's kind of a novel and emerging vector that we're trying to get a handle on understanding. And it's really different than the traditional vectors that spread species around the globe, like ships or aquaculture transfers, because those are quantified, so you can get data on where boats are going to and from. But with marine debris, you have almost no idea where it's left the shoreline, and then when it lands, you have no idea where it's come from or how long it's been in the water. And so that's partly what made the data from the tsunami so scientifically valuable.
Now, I have you guys for a few more minutes. And first of all, since we are at a live show, I wanted to ask, are there any questions from the audience? Because I've got loads of questions. But if anyone in the audience has questions, now is your time to ask questions of the experts. Oh, we've got one! If you will say your question, I will repeat it into the microphone to make sure it gets on the recording.
So are you seeing bioaccumulation across trophic levels?
The question is, do you see bioaccumulation of plastics across trophic levels? And that means, you might have a plastic in a plankton, which then, concentrates in a fish, which is then eaten by another fish, and you get more plastic.
Yeah, that's a really great question, and actually one that Chelsea and I have worked on together and thought about a little bit together. And unfortunately, the answer is I don't know, or we don't know, and it depends. And so you can imagine that we often think about bioaccumulation from a chemical perspective, and so we know things like mercury bioaccumulates. So bioaccumulation is over time, and biomagnification is through trophic scales. And so we don't know either. So there are cases where we actually find that younger birds have higher levels of plastics than their parents. Any guesses why? Because those parents are actually offloading to their chicks. So the parents, you can imagine, are going out into the plastic buffet, and they're actually bringing it back, but then they're feeding their chicks the plastic. So the parents are offloading to the chicks, and the chicks have basically only what the parents have given them. And so it kind of skews the bioaccumulation, right? So in that case, we have younger birds with more plastics than the older birds or the breeding birds. So it's not as I would say in simple as from the contaminant perspective. From a biomagnification, which is the trophic level perspective, I think it also depends again. And so we definitely know that there's trophic transfer. So we've done some work in the Faroe Islands where we've looked at predatory birds that eat different seabirds, and we find that the predatory birds that eat birds with more plastic have more plastics themselves. So we know that it's kind of going up, and it's probably lots of examples. But the problem is that it's a physical contaminant. So you can imagine that a zooplankton might accumulate high levels of plastics, and it could go into a fish that would accumulate those levels of plastic as well, depending on the gut morphology. But then if it goes into a seabird, the gut is just physically bigger, and so it might biomagnify up to a point, but then the top predators, their physical gut is just bigger. So you can imagine that a zooplankton gut is very small, whereas a bird gut, when this is going to be a little gross for some people, but their intestine I can actually put my finger in. So you can imagine that the tip of my finger can pass from the stomach and through the pyloric sphincter into the intestine. So anything that's smaller than that tip of my finger is just going to like right through. And so then, take it up a notch to seals. Take it up a notch again to polar bears, right, where the pyloric sphincter is a lot bigger. So we don't actually expect the biomagnification in the same way as the chemical contaminants because it's this physical passing through. So the things what we've talked about is that we think that there's probably biomagnification up to a point for some size classes, and then it would fall away. But depending on what size class you're talking about, you may have kind of these peaks within the food web and then falls off. But it'll change depending on your size class.
So what you're basically saying is that as an animal gets bigger, its intestine gets bigger, and that means it can pass bigger and bigger plastic particles.
Exactly.
So more gets through.
More gets through, but you also have to imagine that if you're a seal, you're also just more likely to ingest bigger pieces of plastic.
So you're also taking in more.
Yeah, so there's this relationship between the indirect consumption of plastics, which would come up through the prey, but then you also have to kind of pile on the direct consumption. So you can imagine that we have species on the landscape, and I have hunters who've told me that they've opened up animals and found weirdo things in their stomachs. I have hunters who've told me about socks inside polar bear stomachs and towels and other weirdo things. Whales with plastic bags in them. Clearly it didn't get that from a plankton, but it would have all these things together.
I don't know that plankton's life. I guess you do. Anyway. So this is getting very depressing, and I would like to start on a little bit more of an uplifting note. So I wanted to ask all of you, we know the main solution here is to stop using plastic, yes, but we're already using plastic. The reality is we probably won't stop completely. We need to clean it up, and there are these highly touted projects, like the Ocean Cleanup Project, that are not necessarily going well right now. What do we have that we know works for cleaning up plastic?
So I'm gonna turn that question a little bit. So one of the things that I know that plastics can be a downer. I know it's sad to think about plastics in beer. It's not my favorite topic. But one of the things I actually find the most exciting about plastics is that we're in this, what we call this policy window, this space where people are talking about it and people are creating policies about it. And through our work with the seabirds in the North Sea, and work carried out by our colleague Jan van Franeker, they've tracked plastics over time since the 1980s. In the 1980s, they saw a big problem with industrial pellets or nurdles. And
I just love that they're called nurdles. I'm sorry, I need to stop this for a second. Small industrial plastic pellets are called nurdles, and they're the best. All right, continue.
And so when we started seeing these in the seabirds, or when Jan and his team started seeing these in the seabirds, that was actually a great moment where they went and worked with industry and changed some policies, input a lot of new policies, and we actually see nurdles in seabirds decline over time in both the northern hemisphere and the southern hemisphere. And I think that's an amazing story. So we did science, we figured out a problem, we created a policy, we continued on our science to do biomonitoring, and then we were able to do a check and balance whether that policy was effective or not. And so I think we're in this amazing space where all these people are talking about it, and we're talking about different solutions. And I think that there's not one solution. It would be great if there was a silver bullet that we could just put into action. But the truth of the matter is that there are multiple sources. There is going to be multiple solutions. And the most important part about it is that people are actively engaging about it. It's a theme at this conference. It's a theme of the G7. It's being talked about in policy tables. It's being talked about in labs. It's being talked in grad student conferences. It's being talked about at governmental levels. And so, from our perspective, or from my perspective, it's not about plastics or banning plastics. We're really focusing on zero plastic waste. We're not going to get rid of plastics. It's about wise and informed decision making about how do we keep the plastics in the system, how do we keep them useful, and stop the leakage to the environment where they're doing harm.
Well, sadly, we are out of time. So thank you so much to Jennifer Provencher, Christina Simkanin, and Chelsea Rochman. Thank you for being here.
No problem. Thank you.
Thank you.
Thank you.
And thanks all of you for coming out. If you'd like to know more about all the work from these amazing scientists, we will be linking to their papers and their talks at scienceforthepeople.ca. You can also find links to Twitter and Facebook and iTunes. You should follow us. You should subscribe. You should like us. You should write happy reviews about how much you loved this live show. And then you should kick us a few dollars on Patreon to support us. So thank you for listening, and we'll see you next week on Science for the People.
But wait, we're not done. In fact, we've got some things to talk about, and that's why Rochelle is here to join me. Hi, Rochelle.
Hello, Bethany.
Now, I know I was all into celebrating our 500th episode, but it was really only a 500th-ish episode. There are rebroadcasts and renumberings, and really, 500 is just a number. I mean, it's a big number. But in fact, we've got an even bigger anniversary coming up, right?
That is correct. On March 20th, 2019, Science for the People will celebrate its 10-year anniversary. Holy smokes.
Woo!
It's amazing. So Science for the People as a name of the show, I think has only existed since 2013. But before that, that was just a rebrand of a show that was already in existence since 2009, which was previously called Skeptically Speaking. And that show started on March 20th. 2009, and it started at CJSR in Edmonton as primarily a radio show that aired on that campus radio station, but they also pushed it out as a podcast because podcasts were new and exciting, and why the heck not? It was cool, it was interesting, it was a fun way to expand the scope of the show and provide it for a wider range of people, and that's kind of how we came to be a podcast, is a little bit accidental.
But I love that we did it. I mean, I wasn't there, but pioneers, brave
Exactly.
pioneers in the podcasting world. But as the world has changed, so have we. Now, most of our listeners actually access us through the internet as a podcast, far more than ever access us as a radio show. Isn't that right?
That is correct as best as we can tell. The vast majority of our listeners find us online via our podcast feed. We still provide a feed to radio, but it's unclear how many people listen to us there, but it doesn't seem to be that many when we solicit feedback and when we have done surveys in the past.
So we think it's time to make a few changes, you know? But that don't take that to mean that this podcast is ending. The podcast is not ending. Far from it. We love what we do, and we don't plan on stopping anytime soon.
No, that is definitely true. We are, as always, a dedicated bunch of volunteer podcasters who love the topic and love the show that we do. But we do want to change with the times. Now knowing how large our online audience is, it doesn't really make a lot of sense for us to continue creating a weekly radio-style show because it has some challenges.
Yes. For example, some weeks it's really easy to fill an hour with fascinating guests. Other weeks, I mean, some guests are fast talkers, all right? They're fast talkers.
Exactly. Super interesting content, but sometimes we just don't fill the hour. And other times we have enough great content to fill an hour and 15 minutes or an hour and 20 minutes. And instead of having to cut out some really great stuff, we'd like to be able to give that to you.
So, we'd like a little more flexibility. Podcasting has killed the radio stars. So, what are we going to do?
So by March 20th, we will be an online-only show. We're going to no longer produce exactly 60-minute length episodes for radio stations. That doesn't mean you'll necessarily stop hearing episodes from us on radio stations, but you'll likely stop hearing the new episodes as a lot of our existing radio stations transition away from having us as a show because we're no longer going to stick to that rigorous 60-minute exactly time frame. And that will cause some problems for radio. So we're already in the process of letting them know and communicating with them. We're going to provide them with a list of our back catalog so that they can transfer over and have some additional time to move into new content in those slots. But if you want to get new episodes, if you want to guarantee you're getting all the new episodes of Science for the People when they come out, you will need to find us online at scienceforthepeople.ca or using the podcast application of your choice, whether that's Apple Podcasts, whether that's Overcast, Pocket Casts, all the other really great podcast apps out there. Search for us, Science for the People, and it'll pop up as a feed that you can subscribe to.
Check it out. Thank you so much for listening. And we'll see you next week on Science for the People.
Bye!
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.